Hi friends, welcome to my channel. Let's have a look at today's daily challenge problem. Problem 2439. Minimize maximum of array. In this video, we are going to explain two solutions. One is based on binary search and the other is based on mathematical reasoning. First, I'll read through the problem statement to digest the requirement, and then we do the analysis, and finally we share the code and explain them line by line. First, let's look at the problem statement. We are given a zero-indexed array called nums, comprising of n non-negative integers. So in one operation, we can do the following. So we find the index which is greater or equal than 1 and less than n. Then we can decrease the element at index I by 1 and increase corresponding at index I minus 1 by 1, right? In other words, we could balance the two, right? We can put some parts of the number at index I to the number at index I minus 1. So we are required to return the minimum possible value of the maximum integer of nums after performing any number of operations. Here are two examples. Example 2 is very special, and also it's very illuminating. So in this example, the right element 1 is smaller than 10, so we cannot perform the operations above. So that's basically a stable state. And in this case, the largest number is 10, so we're going to return 10, right? So it's also the minimum possible maximum of the array. In the first example, we notice that 7, 3, and 7, these two numbers, so 7 is larger than 3, and then we can put, their sum is 10, right? We can put 2 of 7 to 3, so we get 5, 5. So we're going to get 5, 5, and 1, 6. And then 1, 6, 6 is larger than 1, so we can put 3 to 1, we get a 4, so we get a 4, 3, right? So we get a 5, 5, 4, 3. So in this case, 5, 5, 4, 3, the right ones are less than the left ones, so this is a sort of stable state, so we're going to return 5. But here also provides an explanation. However, this does the job, but it still does not touch the core of the final state. So we are going to demonstrate this point when we explain the second solution method using mathematical reasoning. With that said, let's look at the constraints. First, the n is the length of this list nums. So it's bounded below by 2 and bounded above by 10 to the power 5. So basically 10 to the power 5 determines the problem size upper bound. Thirdly, the elements in the list is non-negative and bounded above by a large number. So here is 10 to the power 9. So with that said, we are ready to look at our plan or analysis. First, our treatments here are the following. The one is binary search, and the second one is mathematical reasoning and find max running average. So we're going to explain all this in details. Here, first, let me make an observation. So if AI is less than or equal to AI plus 1, then we could decrement the latter to increment the former until the former, that is AI, is no less than AI plus 1. As such, we notice that their sum does not change. This is the first. So overall, we could make the array a non-decreasing one. So we are going to use this point to write the second short solution format after demonstrating this key observation later. So for the binary search treatment, we do not need, notice the quotation mark, we do not need to pay attention to the details up to the above extent. We just need to notice that the values can only flow from right to left, right? So you can decrement the number at a index, and then you can increment the corresponding element next to in this index, but to the left. So this shall be sufficient. So you can see this point in the Boolean function we are going to write in the binary search. So with that said, we are ready to look at the binary search treatment first. Binary search. So in this method, so there's going to be 2 steps. The first step is that we are going to write a Boolean function to produce order, and secondly, we are going to do the routine binary search. But the key point is how to determine search range, how to do shrinkage, and how to do return. And now let's begin. So step 1. So the Boolean function. This is used to produce the order of monotonicity so that we can do binary search. So here we can call this function conform. So we'll accept an argument key. So basically this returns if we could make all elements in nums less than or equal to k, right? So because we know this operation, we could move some value from the element from right to left. Then we are going to write this from right to left, or iterate from left to left. So here we are going to use a remainder that's called r. So originally 0. Then we are going to iterate from right to left for I in range. So the last index is n-1, right? And we are going to end at index 1. So we write 0 here. So the decrement is 1, right? So we write -1 here. Then the current number is nums as the current index, right? So we are going to check if the remainder plus the current number is less than or equal to k, right? If their sum is bounded above by k, right? So we can make the current element at index I less than or equal to k, right? And then we're going to set the remainder to be 0 and then continue. Otherwise, so in order to make the last element k, right? So because the current is the sum is r plus current, so we make the number at index I to be k, and then we are going to have a remainder, right? The remainder will be current. Let's see, will be current, the remainder, the previous remainder plus current minus k, right? And then after this iteration, what we are going to return is that we're going to return because if we have a remainder, we need to add to the very left, that is the element at the index 0. Because at the index 0, we cannot move to the left anymore. So any cumulative remainders from the right should be added to the first one. So we're going to check if r plus nums 0 is less than or equal to k. If this is so we can form. In other words, we can make all elements in nums less or equal than k. Otherwise, we cannot, right? So this is a Boolean function. So step 2 is the binary search. We're going to do the following things. First, search range. Second, shrinkage. Lastly, return. Right. So with the above binary Boolean function, so we are ready to do this. First, notice that the element is bounded below by 0, so we can have low equals 0, right? High. So the largest possible value is given by 10 to the power 5, or we can use the maximum of nums, right? So we can add 1 if we like. So low is 0, high is max of nums, or plus 1. Just you can plus some larger one, just as large as possible. Will still if you no less than this max nums, it will do the job, but that's just a plus 1 here. So next we are ready to do the shrinkage. We write low if low less than high. So notice here we are writing low strictly less than high, so that we can have avoid stacking. So now we are going to compute the mid. So we are going to do this: high minus low interdivision by 2, right? In other words, we start from very low. If it's low, actually this function is going to be false, right? So if it's very high, so the function will be true, right? If it's larger than this max, so automatically all element in the nums is less than this number, right? So then what we are going to do, so here let me make one more remark. So the problem asks us to find the min key such that can form key is true, right? So we want to find the min key such that this function returns true. So now we do this check: if can form mid. If this is true, it means that we can still has hope to make it smaller. So we write high equals mid. Here we didn't write mid minus 1. The reason is if mid minus 1 is false, then all the below ones will be false. We cannot come back. So we write high equals mid. This makes that if we consider high always make this can form true, right? Otherwise, so if this is not true, so it means that mid is too small. So we're going to make low equals mid plus 1. Because mid is false, so we need to do, here we cannot do mid itself, we do mid plus 1. So this way, according to the explanation here in this if block, so we should return high for this problem. So before we make any further comments, let's first do a check for this problem. Here n, okay, so let me write n equals length of nums. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So this is about the binary search solution. So notice that the paradigm here is important. So we define Boolean function to produce order or monotonicity, and then we transform this problem to be an optimization problem, and then we use binary search. So here we return high. Actually, in this problem, so we can also return low due to the logic here. If we return low, it's also true, because it turns out in this problem, low and high will converge or being the same. So let's check that. So, but this is better to. This is just a comment. It's better to return high in this specific problem. So with that said, I guess that's about it for this binary search method. So next, I'm going to explain another method based on computing the running average. So here, I'm going to change this one to be version v1, and then this one to be math with and find max running average. So here the coding is not that essential. The thing is, how could we digest the method? I want to add some thing here. So we just mentioned at the very beginning. So if AI is less than or equal to AI plus 1, and then we could finally make the list non-increasing. So here, actually, this can be easily proved mathematically. Here, let me use a specific example to fix the idea. Let's use example 1. So you have 3, 7, 1. Let me pick 1. Let's see, 20. So we want to see. We can make it non and increasing. So let's see. If we have these two numbers, so because the letter is larger, so we can. Their sum is 10, so we can make them 5, 5, right? Then 1 and 20, the 20 is larger, so their sum is 21, so we can make this one 11 and this one 10, right? And then we can continue. The reason is that 5 is smaller than 11, right? So we can, and their sum is 8, so we can make it 8, 8, and then we have 10, right? Then we continue. 10 is larger than 8, so we can make it 9, 9. So we have 5, 8, 9, 9. So the way to get the rest, the final state, non-increasing state, is not unique. So here we have 5 and 8. 8 is larger, so their sum is 13. So we have 7, 6, and then we have 9, 9, right? Then we can continue the procedure, right? So we have 9 is larger than 6. Their sum is 15. So we're going to have 6, 7, 6, not 6. 6 plus 9 is 15. We get 8 and 7, right? Then we get 9. So we continue, right? So here we have 7, 8, and we let's look at this first, maybe. So we're going to have 7, 8, 7, 9. Their sum is 18, so we get 8, 8, right? And then, so 7 and 8, 8 is larger, so we can make it 8, 7, and 8, 8, right? Then we continue, just switch 7 and 8 in effect, so we get 8, 8, 8, and 7, right? This is a non-increasing sequence, right? So their sum originally is 31, right? So again, here is this 39. This is actually very important, because for a non-increasing sequence, their running average will be decreasing, right? So for example, this average is 8, and this 8 is because this is very special. But if you look at the average here is 8, and then if you consider the 4 average is smaller than 8, right? If this 3 have a larger average also than this 3 because decreasing. So this way actually it indicates us we could find max running average for any range, say from I to some j, both inclusive. And however, once their length fixed, right? So then their average will be decreased. For example, the average from I to j is larger than the average from I plus 1 to j plus 1, right? That's the thing. So overall, we just need to, for each fixed length, we just need to consider the average from left, right? So this is the largest length 1 average. This is largest length 2 average. This is largest length 3 average. This is largest length 4 average. So overall, what we are going to do, so we compute the prefix average, and then pick the maximal one. That's the problem. That's it, right? With that done, so I hope that you have digest the reasoning, or at least you have some feeling. So now let's look at the coding part. As for the coding, it's actually very very simple. You can even write a one-line coding. But here, let's just write in some verbose way to digest the idea. So first, I have a result. We can start from num0, right? So I have result num0, and also the current running average. So it's also num0, right? You just have one element. Then we're going to compute, and so for I in range, say 1 up to, let me also write n equals length of nums up to m, right? So let's maybe do a sum. That's maybe better. So then s plus is the current number, right? So how many terms we have? We have I plus 1 terms, right? So we have the index 0 and up to now I have so the average. So let me write one more line, will be s divided by I plus 1. But here, because we want to find the largest one, we can take the ceil. So math ceil. So then we are going to update the result to be the max of result and the average, right? And then after this iteration, we just need to return the result state. So this is the second solution. So if you like, you can write this code in sort of one line, but that's not what we pursue here. We want to explain the logic. Now let's look at the test. Yeah, it passes one example. Now let's look at the second one. The second one is very special. Let's see. Yeah, it passes the second one also. Now let's look at the generic case. Wrong answer. What's the problem? So let's see. The average, the result, and then let's see how many terms. So we have 1, I equals 1, and then 1 plus I plus 1. Let's see, average, then num0, or I in range 1 plus n, s, the if average will be ceil. Oh, here I guess this is the problem. We need to do a check. If s integer division by I plus 1 is larger than the result, previous one, and then we are going to do this. So we're going to do result average. So let's see. Let me change a little bit here. So we're going to do because we used integer division pattern, so we are going to do this, and then we are going to do result equals max result, and then a math. We are going to compute the ceiling. So s, so division. So we do float division. So it's I plus 1. So this will be correct because there's a different by 1 problem. So now let's check again. Yeah, it passes all the cases. So now let's test it again. Yeah, so that's about it for this second version. So as we mentioned, it can simplify this a little bit, yeah, to make it shorter. But the second method, actually, we need to realize this key observation or the reasoning. Once this done, so this problem can be very straightforward or simple in some sense. And the binary search method here we don't need to realize the final state of this list after the operations allowed. However, if we carefully observe this one, right, it's actually also non-increasing, because we, in some sense, we put all the things flow to the left. So with that said, I guess that's about it for this problem and this video. If you found this explanation useful, you're welcome to share with your friends. Thank you.